reducing agent, and thiosulfate acts as oxidizing agent. Product is iodine and product is sulfate ion. This is ionic reaction and it is a redox reaction, electron transfer reaction, in which reactants have roles. This is reducing agent and this is oxidizing agent. But take my word, it takes lots of time to complete. So in order to increase its rate, we use here catalyst, and that is iron. And in which oxidation state? In which bonded state? +3 oxidation state. And what happens? This iron as catalyst, this ferric ion as catalyst takes this reaction via two-step path. In first step, what happens? It reacts with one of the reactant, that is iodide. Because iodine is reducing agent, ferric ion has to act as oxidizing agent, and it will act. Why it will act? Because it is in its higher oxidation state, and if an element is in shows two oxidation states, in higher oxidation state it can act as oxidizing agent depending on other reactant with which nature of other reactant with which it is reacting. Since iodide is reducing agent, so it has to act as oxidizing agent. Here it will lead to formation of one product of the reaction, and ferric ion will change its oxidation state. Iron will change its oxidation state. It will now come in +2. Iodide is reducing agent. Iron 3+ has to act as oxidizing agent. Will it act? Yes, it will act. Why? Because it has one more oxidation state available in which it can exist, that is +2. Now in second step, this modified catalyst, which is in different oxidation state, will react with one more reactant, that is S2O8 thiosulfate, and it will reduce it to sulfate ion, and itself it will get oxidized to ferric ion. Now see here, it is oxidizing agent. Thiosulfate ion is oxidizing agent. Fe+ has to act as reducing agent, and it will act as reducing agent because it has one more oxidation state available to it, that is +3, in which it can get oxidized, thereby acting as a reducing agent. Now do check. Iron in first step is involved. Yeah, it plays its role as iron 3+ oxidizing agent, and in second step iron species same but in different oxidation state, and it here varies its role. It plays role of a reducing agent, and in first step it converts one of the reactant into product, and in second step its modified form changes another reactant into product. So this is two-step path. The two-step path provided to this reaction by catalyst, which is a transition element, and because of its ability to show variable oxidation state. Likewise, I can give so many explanations by which I can justify that transition element and their compounds are used as catalyst. Like in manufacture of sulfuric acid by contact process, their vanadium pentoxide is used as catalyst, and vanadium pentoxide takes reaction via two-step path. In first, vanadium pentoxide reacts with sulfur dioxide, converts into sulfur trioxide, and in second step, modified form of catalyst, which is V2O4, in which vanadium is present in +4 oxidation state, unstable oxidation state. It reacts with one more reactant, oxygen, changes its modified form into its original form, vanadium pentoxide. In this way, catalyst is regained in its original form. Similarly, I can give one more explanation where I will justify that transition element and its compound can act as a catalyst, but here I will take advantage of solid state. In solid state, you might have read that transition element compounds, transition element oxides, sulfides, they are usually semiconductors, and their band gap lies in ultraviolet and visible region. So when ultraviolet and visible region falls on this semiconductor, which is transition metal compound, oxide or sulfide, what happens? Provided the energy of ultraviolet and visible light is equal to energy of matches with energy of band gap, it will absorb ultraviolet and visible light. And what is the response? Response will be electrons from valence band will excite to conduction band, and electrons present in conduction band will act as reducing agents. They will reduce any substance, and holes present in valence band will act as oxidizing agents. They will oxidize any reactant, thereby carrying reduction of one reactant and oxidation of another reactant, but indirect reduction oxidation, because it is occurring through this excited semiconductor which acts as a photocatalyst. Similarly, one more explanation I can give, where transition element in its combined form is used as an electrocatalyst. You stimulate it by a potential, and this potential brings changes in its band structure such that its redox ability changes, and its redox ability its changed redox activity, its changed redox potentials may now catalyze any oxidation reduction reaction. So do remember, in your 11th and 12th class, do remember only two explanations, at least one, presence of unpure d electrons, and another, variable oxidation state. And if I can summarize, I will say that you can define transition element and its compounds as a catalyst in many ways. First thing first, you can express it as a heterogeneous catalyst. For example, here nickel is solid, while as reactants and products are gases. And in the reaction where reactants and products are gases and catalyst is in different phase solid, it is heterogeneous catalysis, and it is nickel here is a heterogeneous catalyst. So you can say we can define transition element and its compounds as catalyst by saying that it has ability to act as a heterogeneous catalyst, it has ability to play as oxidizing agent or as reducing agent in different oxidation state, or it can act as a photocatalyst, or it can act as an electrocatalyst. So this was all about catalytic properties of transition elements. I hope you understood it and you learned many ideas on basis of which you can solve objectives related to this topic. Thank you.